So I think that, well, John arrived, so we can start. Let's interpret this way. So, good morning, good afternoon, good evening, everyone. I'm Gaetano Cascini, Politecnico di Milano, and I'm very happy to have the chance to chair this session dedicated to designers' activity analysis. We have 5 presentations now. We know the format of this unusual edition of the design conference that still, I mean, I think that it is allowing us to share the results of our work, exchange ideas. So, I mean, given the context, I'm appreciating very much what the organizers have prepared for us. Just from a practical perspective, I as already agreed with the presenters, I will let play one video at a time. Right after each video, should the participants have any clarification question, pay attention, just clarification question, I would make it right after the video, just to be more directly connected with the video play. And right after, we will proceed with the next one. And at the end, of course, we will have roughly half an hour for deeper discussion, questions, and further responses. Okay, so let's start with the first presentation. The author written in the slide here is Aurora Berni, who is an assistant research fellow at Libera University of Bolzano, but here her supervisor, Yuri Borgianni, will participate in the discussion on her behalf. Please, Yuri. Ivan.
Good morning or good afternoon to everyone. My name is Aurora Berni and I am a PhD student at the Free University of Bolzano. Today, I want to present you an investigation on design evaluation supported by eye tracking technology. Let's get started. So, within the design process, products are often presented by means of graphic representations, and sight is the main sense through which potential users can perceive them. In case of creative products, their unusual characteristics can be hard to be perceived through graphic representations, and these can lead to users' misinterpretation of their original design intentions and intended affordances. So the question is, can different forms of representation of a creative product affect observers' understanding of original design intention and his or her visual behavior? So the aim of the study is to investigate the relationship between static and dynamic representation and to see how they affect perceived affordances and observers' visual behavior. Therefore, we conducted an experiment showing participants pictures and videos of 6 creative products as dynamic and static stimuli. A remote eye tracking was used to gain visual quantitative data, while interviews to participants have been used to collect qualitative data. In this way, we had both information on participants' attention and their understanding of each stimuli. So let's do an example. If I ask you to look at this picture and to tell me what the exact function of this product is, maybe you will fail. But if I play the video, everything becomes clear. From the comparison of pictures and videos as static and dynamic stimuli, emerged that the dynamic nature of videos help to direct the user's attention towards crucial elements to capture design intentions and understanding of functionalities. In particular, here is an example of how an observer shifts his or her attention in a short video. As you can see, this plot helps to identify gaze movements. Another interesting point regards area of interest. In particular, we use area of interest to get information about where exactly the observer focused their attention, and we use them both in pictures and videos, so in static and dynamic stimuli. The use of dynamic areas of interest is fully exploited in design research so far. The importance of dynamic areas of interest is that they follow the movement of the salient aspects of the product shown by the stimuli, as we can see from this video. In particular, comparing static and dynamic areas of interest, we observe that in videos, those areas of interest of crucial feature for the understanding of the product were faster detected by observers. So these findings can have an impact in the design studies of emotions, user experience, and human-computer interaction. In fact, in these fields, form of representations need to be chosen accurately to achieve reliable evaluators' feedback. Thank you for your kind attention.
Good. Thank you, Aurora and Yuri. I don't know whether from the audience there are any immediate clarification question about this presentation, this video. Doesn't look like. So if not, then I will proceed with the next presentation delivered by Hanna Nolte. Hanna is a PhD student at Penn State University, and the video is ready to go. Please, Ivan.
Hello, my name is Hannah Nolte. In this presentation, we'll look at identifying stress signatures across the engineering design process, perceived stress during concept generation, concept selection, and prototyping. Engineering design is a highly complex and cognitive process. This is well demonstrated by the fact that engineers rely on multiple cognitive skills throughout design. And according to Alexu et al. And Dinner et al., a number of complex cognitive processes must be leveraged for a designer to successfully complete a design task. These skills can include anything from problem solving and mathematical modeling to creativity and innovation, among many others. In addition to the fact that engineers must rely on multiple cognitive skills to successfully complete design, the high complexity of design is also contributed to by the fact that design problems are inherently complex. As described by Dem et al. And Kanya et al., design problems are often vague and ambiguous, constantly evolving, and influenced by internal and external pressures, all of which collectively increase the inherent complexity of design. This high reliance on cognitive abilities is likely an important contributor to the mental stress experienced by engineers. Recent research by Epson and Jensen has found that engineering professionals are experiencing increasing stress. While the stress of engineering professionals could be impacted by many contextual factors, it is likely that this increase in stress is due to the relatively new demands of modern engineering. These new demands are more focused on engineers' cognitive skills and abilities than they have been in the past. Engineering students are also experiencing increasing amounts of stress, and according to Foster and Spencer, engineering student stress is to the level that associated negative health measures are being observed. Since the work of engineering students and professionals has great similarity and involves multiple complex cognitive processes, it is likely that the type of work engineering designers do is contributing to their increasing amounts of stress. Understanding designers' cognitive stress is important because repeated short-term and chronic cognitive stress can negatively impact designers' health. While short-term stress can lead to increased motivation and creativity, chronic stress can have physical health consequences like lowered immunity, higher susceptibility to infections, and cardiac issues. Additionally, chronic stress is also one of the leading causes of burnout in professionals. This study investigated the cognitive experience and mental stress of student designers during 3 separate design tasks. 25 students from an introductory engineering design course completed the 3 tasks, including a concept generation task in which they brainstormed ideas for office exercise equipment, a concept selection task in which they rated designs for an accessible water fountain, and a prototyping task in which they built a knee brace. All three design tasks utilized the following methodology. Students would first watch a short video to stabilize their stress state, after which they would take a pre-task survey consisting of a modified version of the NASA RTLX and a physical arousal questionnaire, after which they would have 10 minutes to complete the design task. After the 10 minutes were up, students then took the post-task survey, which consisted of questions about the design task and the stress they experienced during the design task, in addition to repeating the modified NASA RTLX and the PAQ. This study confirmed that design is a highly cognitive process and that each design task produces a unique stress experience for students. When students' average scores were ranked from highest to lowest for all sub-items of the modified NASA Raw Task Load Index, it was found that for concept generation, students' highest score was for mental demand, which was then followed by effort and then stress. Similarly, in concept selection, students' highest score was again for mental demand followed by effort. However, their third-ranked score was for temporal demand. And lastly, for prototyping, students' highest score was for temporal demand, then followed by effort and mental demand. Additionally, students' top perceived stressor varied by task. For concept generation, it was not enough ideas. For concept selection, it was I could not choose just one. And for prototyping, it was not enough time. The results of this study can be used to not only improve design instruction, but also to mitigate the stress of novice designers. The paper corresponding to this presentation offers many suggestions to help design instructors apply the results of this study to their design courses. Additionally, further research has been conducted by the research team on this topic, which we would be happy to discuss further, either by reaching out to us or during the discussion session. Thank you.
Thank you, Anna. Nice video. So again, I'm trying to be more timely since questions for Yuri and Aurora emerged afterwards, but now it's time for a clarification question for Hannah, if any. I will leave a little bit of time for that. Feel free to speak in case. So Lorenzo says, were success conditions set for the participants or a reward scenario? Hannah.
Participants received participation points for participating in their activities, but they were not judged on their performance or the outcomes.
Okay, good, clear, sharp. I think that, well, I promised one clarification question only. There will be more time afterwards. So let's move to the third presentation, which is delivered by Sonia Vieira and John Gero. Well, I don't think that John requires any introduction. Sonia has a PhD at University of Delft and now has a postdoc position at Politecnico di Milano, and they are both working on this project since several years now. The video, even.
Hi, I'm John Gero.
Hello, I'm Sonia Vieira.
We're a team of design scientists from multiple institutions.
And we are here, pleased to be here during this time of physical restrictions, sharing this virtual space with you to present our work. We present results from an experiment studying novice and experienced professional designers' neurophysiological activation differences when performing two prototypical tasks, problem solving and sketching. We have been studying neurophysiological activations of professional designers for multiple domains. Today we report results from studying 36 professional designers, 20 novice designers with up to 5 years of design experience, and 16 experienced designers with more than 5 years of design experience. We designed an experiment consisting of a block of 3 layout design tasks, preceded by a familiarizing pre-task and extended to a 4th open design task. In this open design task, we present results comparing the constraint task based on problem solving, and an open design task based on sketching. In this task, participants were asked to design a future personal entertainment system. Here we show some examples of designs. We use a 14-channel EEG headset using an international standard placement. Here you see the setup. A physical interface was built with magnetic material for performing the tasks. Audio, video, and EEG measurements recording were streamed using Panopto. The channels we are measuring are shown in these plots, distributed on the left and right hemispheres in mirror locations. Measurements for each lateral are shown for the 5 tasks. From the novice design on the left, results indicate that the open task, the blue line, shows higher activation than the constraint task, the orange line. In the channel FC6, associated with searching for originality, channel P8 associated with sketching, channels O1 associated with visual mental imagery, and O2 associated with visual spatial information processing in the nervous cortex, and P7 associated with attention to semantic relations. It's where we found statistical significant differences between the open task and the constrained task. The sketching task shows detached activations from the other tasks, as you can see. From the experienced designers on the right, results indicate that the open task, the blue line, shows higher activation than the constrained task, the orange line, also for channel FC6 and channel O1, associated first with originality and the second with visual mental imagery. The experienced designers show higher activation across all channels than the novice designers in this particular task.
So designing is an activity that occurs over time, and we expect within that different kinds of cognitive acts will occur. So we've divided the design session into 10 deciles, and now we're looking at the differences between the closed task and the open task for novice designers, and we can see here quite significant differences at different points across time. We can see the same with experienced designers, where again, this is the information across time demonstrating that different activations occur at different times during the design process. So what have we learned from running this kind of experiment? Firstly, that constrained and open design tasks produce quite different levels of activations in different regions of the brain. And this implies that the designers are using different cognitive activations themselves in carrying out their designs. Secondly, that novice and experienced designers look very different. Thirdly, that experienced designers show a much higher level of activation than novices, and that the temporal distribution of novices and experienced designers are quite different. So this is the beginning of what appears to be a major direction that allows us to compare cognitive with neurophysiological behavior. We need to specify that we've learned that we were funded by the Portuguese Foundation for Science and Technology and the US National Science Foundation. Goodbye.
Goodbye.
Thanks, Sonia and John. Again, room for one clarification question, one from Yuri. Are there any major time-dependent similarities across groups?
Time-dependent similarities across groups.
Okay. Perhaps I can answer that.
Yeah.
There are similarities and differences. The similarities relate to some more fundamental cognitive behaviors. And the differences are a mixture of different areas of the brain and different networks being evoked and across different times. So there's a significant implication here, which is that education and experience change the way in which a designer's brain responds to design tasks.
Thank you. I don't know, Sonia, you were about to add anything or?
It's my feeling that Yuri wants to know more about the time they spend in each task, if it's similar or if it varies. This is my impression.
No, I mean, I understand that Yuri was asking about similarities across the groups, so novice and experienced ones.
Yeah, that's fine. Okay. Perfect then.
Okay, good. Thank you. And we can move to the next presentation by Bunyaporn Puripanyakun. Sorry, I do apologize for not pronouncing your name well, but it's important that she is a PhD student at Strathclyde, and we can play also her video now.
Good afternoon, everyone. My name is Anyapon Puripanyakun, PhD student from University of Strathclyde. Today, I will talk about the effect of time pressure on dexterous operation performance. In everyday life, we usually see a rush causing unintentional mistakes from using interface. For example, car accident and target error. However, there is a little knowledge on how it exactly impacts performance accuracy. The study will examine this effect, comparing between types of interface. And finally, we will propose insight into design composition. I designed to use a keyboard for a fixed interface and a jigsaw puzzle as a dynamic and movable interface. In the experiment, require eye and hand coordination. The first task is similar to a typing task, but it requires more perception due to participants have to type Thai words with an English keyboard. They need to learn a new lesson, the same as the second task that requires cognitive ability to form jigsaw pieces with dexterity. There are 4 trials for each session, the normal and the time pressure. In this study, I recorded the time and the output, then analyzed the speed and accuracy, as well as error patterns. For the time pressure situation in trial 528, I set the countdown timer in descending. Now, let's look at the result. There are 21 persons participating in this study. More than half can touch typing. It was found that they perform tasks at their own pace, though having different in. From the graph on task 1, there was a significant difference between the 2 sessions. Though the speed seemed to increase from experience, the accuracy was degraded from the time stretch. After being aware of error, the participants tried to rectify the situation, so the error rate fluctuated during the test. For the moving interface, the performance was presented separately because of using 2 sets of a jigsaw. However, the effect of time pressure was a similar trend. The average speed between the 2 sessions also has a significant difference. As this mission requires a higher degree of mental energy, the results show that participants perform it slower than task 1.
Is it finished now? Yes.
Comparing the performance between the 2 tasks, it was found that a speed increment on task 1 appeared to be higher than task 2 and explicitly developed in the time pressure. It can be seen that on task 2, the graph remained rising from the start to trial 3. then fall dramatically. This implies that users require more time to learn, and their performance are so sensitive to the time stress. In other words, a fixed interface provides better performance. Let's talk about error pattern and user strategy. For task 1, there are 7 error patterns occur, such as pressing the wrong buttons, pressing incorrect order. As each word has a different root, it affects the accuracy differently. While in task 2, the error occurs from the wrong position and wrong direction. It was found that participants tend to start at the base in the first place and cluster pieces together. Ultimately, some recommendations are provided. For the fixed interface, the layout should have appropriate proximity, the sequence of tasks should be smooth, and the feedback should be immediately provided. For the moving interface, decrease the interface diversity and offer distinguishing features to facilitate the orientation. In summary, time stress damage finger movement accuracy and information processing of temporal and spatial awareness. The fixed interface lessen human mental workload and offer robust performance in the time pressure. The use of a fixed interface could utilize human perceptive sense and spatial memory. Designing an effective interface could enhance the user experience. Therefore, we plan to investigate the interface design for IC and peripheral interaction in the future. Thank you for your attention. Please feel free to ask some questions.
Excellent. Thank you for the video. Any questions from the audience, from the participants? Just clarification questions for Monia. We have one from Yuri. Which of the experimental conditions you think is more similar to a design task, with or without time pressure?
Experimental condition. I think that in the designing task, designer require cognitive ability and some creative thinking, but in the task, in my experiment, just perform the task under the same procedure, and it's quite later problem solving for the jigsaw task. So I think this experiment is suitable for the user, not for the designer. Is that
okay? Not from the design perspective, then. Okay.
Time pressure.
I think that we can elaborate further this time pressure condition also, because it was somehow relevant also in another presentation before. But I would proceed with the 5th presentation of this session.
Okay.
And we will kick back to the general discussion afterwards. So the 5th presenter is Samuele Colombo, young researchers at Politecnico di Torino, also working on neuroscience related to design analysis. So please, Ivan, Samuele's video.
Hello to everybody. Thank you for being connected here for this presentation. I am Samuele Colombo, a PhD student from the Politecnico di Torino, and I present this research, which is the result of a collaboration with the University of Turin and the Luleå Technological University. We talk about neurophysiological evidence in idea generation, differences between designers and engineers. In literature, some of designers' internal and subconscious aspects are overlooked. Scholars are moving towards a neurophysiological approach. The limitation of this approach is that, to be rigorous, a circumscribed reasoning should be isolated to study it individually. This work starts from the creativity as a feature that most identifies design activities involving different cognitive processes. Given the multidisciplinary nature of the area in which the project works, it was necessary to set up the analysis of the literature by macro areas in order to understand what and how to study. In this slide, only the main references are shown. Two main cognitive processes are identified in the generation of ideas: convergent and divergent thinking. They are mainly investigated by the electroencephalogram, EEG, stating the presence of a top-down inhibition. The literature for ocular activities in this context is still in its infancy, but it seems that during problem-solving activities, people tend to look backward. The aims of this research are to answer the two questions that introduce the innovative features of this work. First, if the combined use of EEG and eye tracker allows to identify neurophysiological activities during tasks related to the divergent thinking, and if they are consistent. Then, if these values allow to highlight differences related to educational background. The experiment involved 40 volunteer students from the Luleå Technological University with different backgrounds in order to identify the engineering designers and other engineers. The experiment involved a single task presented under two conditions: the alternative use task that consists in the presentation of everyday objects for which in the common condition is required to find a common use, while in the common condition it is required to find the most unusual use for the object. These stimuli presented were 40, divided in two blocks of 20 items each, corresponding to the two conditions. The presentation has been set representing the name of the objects. The sequence of stimuli and blocks is shown in this figure, and the succession of the two conditions has been counterbalanced between participants. The main equipment consists of a 32-channel EEG and a remote infrared eye tracker located just below the desktop. In addition, devices or other support tools have been used as represented, allowing both behavioral and neurophysiological measurements to be collected. The analysis of the data are mainly distinguished between the measurement from the EEG and the eye tracker, and are reported in detail. For the EEG, we have focused on the variable derived from the alpha power. For the eye tracker, on different measurements calculated by the areas of interest. The results derived from the analysis of EEG data confirm the main evidence of the literature. In addition, the innovative feature related to the differences in educational background is matched by significant differences between designers and engineers in both conditions, emphasized in the uncommon condition. The analyses of eye tracker were significant, show that the left eye direction is preferred during this task, especially for the group of designers. In conclusion, the results of this research are in line with the literature. The innovative elements have been shown to be significant, validating the initial assumptions related to the robustness acquired using EEG and eye tracker and the difference related to the educational background. Thank you for your attention, and for any more detailed information, I ask you to contact me by email.
Okay, so good. Before starting the overall discussion, I will also allow for some clarification question to Samuele. I would first start with Sonia's one and then back to John's one. That probably is more general, useful for discussion also in other cases, if you allow me, John. So Sonia is asking, did you also look at the other frequency bands beyond what you presented in the video?
We are analyzing the other frequency bands in this period after we wrote this paper, because for the literature we analyzed that the most evidence are related to the alpha power.
Okay.
Okay. Okay, thank you, Samuele. So time now to start with questions to any of the presenters, so it's nice to see if also other participants would like to present their own comments or questions to the videos we just watched. But I will start from what John posted in the chat. The question is specifically dedicated to Samuel again, and well, I had a similar doubts. So I was wondering how much the differences that you measured are, let me say, between engineers and designers are to be considered in general or relevant for a design activity. And somehow John is asking, how much do you think that the alternative uses task is a proxy for this?
We consider the IoT task as a proxy of the idea generation, that is one microphase of the design. Obviously, can you hear me?
Yes.
Yeah, we can hear you. Go ahead.
We decide to isolate. Okay.
No.
We decide to isolate the idea generation. Can you hear me? Okay.
We can hear you. It seems that we have a certain delay, so this is why we are a bit puzzled, because you move and the audio comes later.
Okay, sorry. So our choice was made by the neuropsychologists that are in our team, that said to understand the neurocognitive processes that usually comes to play in a design activity, design process, they are a lot of construct and cognitive processes. We decide to study it from the atoms phases that could be isolated. So we decide that it could be reasonable before to fragmented the design process in these phase and try to replicate a similar condition. And the most used to evaluate the generation of idea as a brainstorming could be in the neuropsychology, the IUT.
Yeah, can I make a comment?
Sure, please.
I'm not convinced that the alternative uses test reflects idea generation in design. And the reason I have this concern is that the alternative uses test is completely decontextualized. In design, everything is always connected, particularly to what you've just been doing. And when we study the cognitive behavior of designers, we find that idea generation is not a single act, which the AUT test is about, but rather is embedded in other acts, and those change what's happening. So the ideas that you generate actually change everything around it. And I think that's what's missing in these tests.
I don't know whether somewhere you want to have a short reply to this, but then maybe you can continue on a parallel.
Obviously, it's a good point that to understand why we decide to use this task. But for us, for the strictly condition related to the use of electroencephalogram or other neurophysiological tools, it was quite required to have a very, very little span of reasoning that the people that are attending the task could have. For example, we reduced the role of the words translating in the stimuli in the mother tongue of the participant to avoid every type of reasoning related to translation. Or for our approach, the main aim was to reduce everything that could affect the direction of the participant thinking about a generation of idea. Obviously, it is not like in an idea generation in brainstorming, because we're not supposed to have the some limits or similar things. But for us, it is a way to understand how we reach creativity and how our brain works in that activity. For example, the main conclusion could be that maybe you could prefer to work in a white room to generate your idea, to avoid your stimuli from the your external stimuli. For example, that could be obviously a strong assumption that could be validated eventually in further studies, but it could be a starting point for this. Okay.
Thank you so much. Well, on the same page, I would report also Alberto's comment saying that the study uses the AUT test to quantify the generation of ideas, but during the process of design, many elements are interacting fluently, And then he ends with a question: is it possible to assume that there are differences when actually the experiment is very isolated? And I think that this is exactly on the same page. But I would like to allow also others to make their own comments. So please allow me to move to other questions. Maybe in this case, going backwards to Munia, I mean, there was a question on this context, and maybe you can clarify further. To what extent your second task is connected with design? You wrote something in the chat, but maybe you can elaborate a bit more by words. To what extent the second task of your experiment is connected to a design activity?
Yes, I think that the second task is the holistic thinking from many information, and this similar to the design task that they have to create something new from the many information, and they need to understand user and have something that facilitate the task. For example, the visual cue or something that help their orientation and navigation to the design on the spatial location. My research is focusing on the human-computer interaction rather than the design task. So I'm not sure my answer is reach your question. Sorry.
It is relevant, of course. The topic might deserve a much broader discussion, but I think that yeah, you are at least touching it definitely. Okay, I will still move backwards, but I will not make a question to Sonia myself. So I would ask others if there are any questions for Sonia and John. And in the meanwhile, I would move back to Hannah. If I remember properly, your experiment involved a 10 minutes task by the students, right? I was wondering, please forgive me if this is not appropriate, but somehow I would associate a certain connection between stress and tiredness. I mean, I know that you are looking not to the short-term stress, but still, I mean, I suppose that there is a certain degree of stress that increases with time. So I was wondering, what was your idea behind why you decided to go with a relatively short duration test? And was it on purpose, or was it just to reduce the time of the experiment? What are you getting, and maybe what are you missing in case? I'm sure you made a proper reflection on it, so I would like to understand a bit better.
So there are a couple of reasons that we chose 10-minute tasks. Part of it is this was done with first-year students as a warm-up activity in their classes. And so similar to the other warm-up activities they had been doing, they were just short in duration. The other reason we used 10 minutes is because we wanted to keep tasks in time. And we were finding that while 10 minutes was sufficient for concept selection and concept generation, it was less sufficient for physical modeling or prototyping. And so we were finding that students really only wanted a short amount of time to do concept selection, but we wanted to keep all of those tasks similar in time. So the average for the 3 tasks that was sufficient enough for them to finish the activities was about 10 minutes. And so limiting the time of the experiment, but also trying to make sure that we reduce the effective time by keeping all tasks at consistent duration.
So, okay, I understand. I mean, that you wanted to focus on what happens in the short term as a part of the study. Thank you.
Yeah, we hope to look at longer duration once we can collect data with students again, but currently that's on hold.
And another question, if you allow me, as far as there are no more in the chat, is about you measured stress indirectly by the survey, by the questionnaire, right? I'm not, again, an expert in this perspective, but I was wondering whether there is any report on the difference between the perceived stress and the actual stress.
So what we did is we collected 2 survey measures for the NASA TLX and the PAQ. The PAQ measure at the time we thought was going to be a good perceived measure of stress, but showed relatively little changes. So we're looking at different ways to get at that physiological stress in the future. But what we're seeing is students are actually perceiving less stress than we think they are experiencing, because they will distribute, or anecdotally, they will show symptoms of stress, like their faces will get redder, they'll take off their sweatshirts because they're getting warmer, but we don't see them reporting that in a physiological questionnaire. So we're hoping to use sensors in the future to get a more objective measure of that, because we think their stress is actually higher than they are reporting. And that's been shown in the literature too, that students have a hard time perceiving changes in stress for short duration tasks.
Yeah, makes sense. And there is also one more from John asking whether the participants were aware of the purpose of the experiment.
So the participants in their consent form were told that the experiment would look at the cognitive experience and stress experience of designing. So they were aware that we were looking at stress, so that we weren't deceiving them, but we didn't remind them before each task. So they were aware of it from the consent form, but we didn't remind them.
Can I just follow that up?
Sure, please.
What do you think the effect of that might have been? That they know you're looking at stress? Because we know, for example, if people go to a doctor, their stress levels go up. If you ask people you're going to take their blood pressure goes up.
Yeah, so part of us telling them was that to prevent that deception of what we were looking at, and that was part of our IRB. But we also think that if we tell them that they were going to look at stress, we think in the short term that might have made a difference. That's why we took their consent and we did the tasks. But relatively, when they start doing the tasks, I think they don't focus as much on stress as we think they do, because they did sign the consent form a while ago, and then they're doing these tasks later. But it definitely could play a part. We would have to run another experiment to understand what that contribution would be.
Thank you.
Mm-hmm.
Thank you, Anna. And then even more backwards, I don't know whether it happened also to you, but I don't see anymore as it used to be. But okay, no problem. Anyway, it was just the list of the presentations. I would like to ask Yuri something about their work on this comparison between the static picture and the video to interpret the way of working, the affordance of a product. And well, I mean, I had 2 doubts that I would like to hear your opinion about. One is how much the comparison between picture and video is somehow representative of the difference between looking to that lead in a real environment, just static, or moving it. And somehow related to this is because if you're comparing picture and video, it is essentially you are using one sense. While when we are in a real environment, we are using all senses. So, I mean, simple evidence, there is the sound, but then, I mean, if you are interacting with something, of course, you have the tactile, the physical interactions, and so forth. So, I mean, what is your point, your elaboration on this regard.
Thank you for your question. I hope you hear me with a nice volume.
Absolutely, yes.
You touched upon an important point, meaning that, of course, although switching from the image to video, you get closer to a full experience, but we are still not there yet. So in each case, through a video, and these are, let me say, we have chosen commercial videos of these strange or innovative products. But in any case, just in order to understand the impact of dynamic effects, we have removed the audio. Also because most of cases the audio was background music, so really it could just distract the audience. So at first, let me say that the first step was a little bit to identify the possibility to conduct this kind of studies. We were able to identify, and this was quite unsurprising, that people understood better the function of the objects when showing videos instead of static pictures. But this doesn't take place consistently. There were differences among products. And of course, we noticed that in videos, some parts of the objects, some areas of interest were most focused on. But we cannot yet say if focusing on those areas of interest was actually the key. Also because we miss a taxonomy of features of areas of interest in order to bring up results that can be considered valid across multiple type of products and not just the ones we have experienced.
Thank you, Yuri. I would use last Sonia's question to allow a very fast response by all presenters, including Sonia. If there are any conclusions or guidelines for designers from your findings, maybe we can just proceed again from Yuri to Anna and so forth, but please try to be short. And then, of course, we will need to close the session, inviting everyone to keep talking in the other moments of the virtual conference. So, Yuri.
The conclusion might be when you design an object, especially if those are quite unusual, keep also in consideration the way you want to communicate them.
Good, nice and sharp. Anna, is there anything that you would like to share as a final statement?
When teaching design to students, we need to be aware that not only are they novices, but they're also experiencing mental stress in addition to their learning. So we have to figure out ways to limit excessive stress in the classroom to better facilitate their retention of material.
Very nice, Anna. Thank you. Sonia, would you, even if you made the question, maybe
I made the question now suddenly, but I'm thinking that perhaps for novice designers, it's important to adapt to the different types of tasks they have at hand and do not stick to the same approach. So be open to that, for example. It's one of them.
Yeah, nice point. Nice point. I don't know whether also, John, you would like to participate in this, or let's move to Munia then. Is there any sort of short statement you would like to conclude about design activities based on your findings?
I think my finding is a knowledge base for the designer to understand the user when they design some interface. The different type of interface providing different results and performance accuracy. So they have to be aware on this.
Okay, thank you. And Samuele, last chance for you to claim on your side.
I think that I spoke a lot before, so for me...
Okay, good. So we are 2 minutes behind the schedule, but not too much, I would say. Thank you all the speakers and also the participants for this nice session. I think that we had the chance to, despite the context, to have a nice interaction. I think that we are all easy to reach by email, if not in the virtual space for gathering together. And so I hope to meet you still in another session, or to be in touch with you by email still on these interesting topics. Good luck. Take care.
Thank you. Thank you. Bye.
Bye.
Bye. Bye.
And thank you, of course, to Ivan for the excellent technical support.
Thank you.
Bye.